Okay, so welcome to differentiation by first principles. So over here, I'll be using a new format to introduce the topics. So instead of using the whiteboard, I'll be going ahead by using this sketchpad. Now over here, we see that we have some sort of parabolic curve. And if you want to find the rate of change or the gradient of any point, what we actually want is this orange line over here, where it says h is approaching 0. Now, before we move on to that, this is what we call the tangent of the line. And to find this in the first place, we need to consider what we call a secant. So this is the purple line that I'm just tracing across over here. And this secant over here is pretty much what we call the average rate of change. And to find out what this is, we can use our basic gradient equation. So what you want over here is y2 minus y1. Sorry, I'll just get a different color. y2 minus y1 minus over x2 minus x1. And this one over here gives us the gradient of the secant over here. And the secant, well, the two coordinates that we're using are over here. So x and f of x, so that's one coordinate over here. And we have another coordinate, I'll just swap to a different color, over here where we have x plus h as the x coordinate and f of x plus h as the y coordinate. So when we slot in our values of y2 and x2, you simply just use the two coordinates that we just specified. So remember how we said y2 was f of x plus h, so that's why we chug it here where y2 is, and down here is where we have x2. And we want to subtract y2 by y1, which is this one over here, and then x2 subtracted by x1. So at the bottom you can see that you have both the x's cancelled out, and at the top you're left with f of x plus h minus f of x. Now this is simply the average rate of change between these 2 points. To actually find out the gradient of the orange line here, the tangent to where this red dot is, what we actually need to do is we need to shorten this secant, we want to shorten the horizontal distance between x and x plus h. And to get these 2 points closer and closer to each other, what we're actually doing is we're trying to make h as small as possible, or make h approach 0, and make it a value very close to 0, or just approximate to 0 in the end. So what we have over here, a way to express h to be very close to 0 is by saying the limit of h approaching 0, and we use the expression for our secant from before. So this is trying to say that we're going to have a secant between two particular points. So maybe this red dot over here and another one over here, except they're infinitely close to each other. Okay, so if you use this formula over here, you should be able to find the derivative function for most functions. So I won't say all of them, but we're going to try it out on polynomials first, because they are often the most simple ones to derive using first principles. Now, down over here, we have a parabolic function, and we want to differentiate this using first principles. Now, to do this, first of all, maybe we'll just reverse our formula up here. So we have f dash of x is equal to the limit of h approaching 0 and this entire expression. Now, doing this all in one go takes a lot of writing time. So what I recommend doing is just focus on this bit for now, just the numerator. So this numerator up here, f of x plus h minus f of x. Just have a look at what this is equal to. So we know f of x is this chunk over here. So what we're going to do is, every time we see x, we're going to slide an x plus h. So we have x squared first, we're going to have x plus h, square this, plus 3, and it's not x anymore, it's x plus h. So we're just going to keep everything in brackets just to keep it all organized. And we're going to subtract by all of f of x. So we're just going to put a bracket over here just to be sure that we're counting for the negative in front. Okay, so now it's just up to us to clean up the algebra over here. So what we're going to be doing is we're going to see if we can cancel any terms before we move on. So just from the get-go, you can see that if you have 4 minus positive 4, those two will cancel out. You may see more, but if you want to play it on the safe side, we can just do some expansion first. So in this binomial expansion over here, we're going to have x squared plus 2xh plus h squared plus 3x plus 3h minus x squared and minus 3x since we're expanding the negative over here. Now we can cancel out a few more terms. So you can see that the positive x squared here and negative x squared will cancel out, as well as this negative 3x and positive 3x. And from here, we are left with 2x h plus h squared plus 3h. Now when you're differentiating by first principles, what you do want to do in the end with your numerator is somehow factorize h out, because what this does is it allows you to cancel out the denominator at the very bottom. So I'll show you what I mean in a moment. So we're just going to factorize this out just to prep this up for the next step. Just move down. And recall that our expression for our gradient function f dash is limit of h approaching 0, and we have the numerator, which we just talked about, h2x plus h plus 3. So we pretty much just slotted all of that in down there, and this is all over h. So the reason why we factorized h out is so that these two can be negated with each other. And one other reason for doing that is because when you make h approach 0 and you make your denominator 0, this means that you end up with an undefined value, which is not what we want. So this is why we want these two to cancel out with each other. And once you do get rid of the h in the denominator, you can actually simply sub in h is equal to 0, so this being over here. And this means that this turns to 0. And since 2x and 3 are independent of 0, independent of h, we can simply say that the gradient function is just 2x plus 3. And it looks like that this checks out with the polynomial rule for differentiation as well, which we'll cover next time.